Hi, y'all.
Hello.
How you doing?
Very well.
Okay, 1 minute.
Hadn't realized this is a Zoom meeting, or I'd have tried to make the sun go away.
All right, good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Engineering Department here at Lehigh University. And welcome to the 7th in our seminar series this fall. A fascinating topic, and we'll hear from Matt Wallace with PPL. The title of the presentation is Distributed Energy Resources, Grid Support Functionality, and the IEEE Standard. This is a very hot subject area, as you know, and it's got a lot of technical ramifications and others too. So a short abstract of what you'll hear today. As DERs become increasingly economical, their popularity grows, and accordingly, DERs have an increasingly consequential impact on the way our society produces and distributes electricity. In recognition of this trend, the electric industry is coalescing around methodologies to leverage distributed assets to work in concert with traditional centralized infrastructure. And this is truly remarkable because what this coalescing means and what shapes and forms it's taking on, and Matt is the ideal person to talk about it to you guys. And Matt has he's talked to this group of students over the years, different cohorts, of course. He's an engineer with PPL Electric Utilities and focused on creating interoperability between DERs and the utilities DERMS system. He has received numerous accolades, including the Smart Electric Power Alliance 2019 Utility of the Year and Public Utilities Fortnightly 2019 Foremost Innovators and 2020 Foremost Innovator in Distributed Generation. And that's terrific, Matt. I think you are, as I said, the ideal person to be talking about this subject. Previously, Matt was with the New York State Public Service Commission. He was in New York, he came to Pennsylvania, and now is in Corpus Christi, Texas. So directionally, he's going the right way, I think. Matt, the floor is yours.
Thank you, Rudy, so much. Mexico is next, I guess. I'll keep that forward. Thank you all so much for this venue, for coming to attend my talk. I really appreciate it. I'll just go into my background a little bit, expanding just slightly on what Rudy said. So I actually originally studied civil engineering and did that for a few years, but the power industry really just seemed like it was on the precipice of massive change. I think change similar to the scale of what we've seen computers do over the last few decades, right? We went from very old, sort of only large institutions had computing power, from the 1970s, things like that. And then we had a revolution in the computer and really the information in general, the information industry in general, where now everyone has a supercomputer in your pocket and we're all connected to anyone in the world and can have instantaneous conversations with anyone. It's all really fantastic. That's the very technology that's bringing me onto your screens here today. And, observing what was occurring in the energy industry, I had graduated college in 2008 and did some civil engineering, some heavy road construction work for a couple of years. And observing what was happening in energy, I had to get into it. So I joined the Public Service Commission and spent 6 years working on the electric distribution systems engineering team, where I was essentially a technical advisor to the policymakers in New York, which is the Public Utility Commission. Up there, they call it the Public Service Commission. So if you're unfamiliar, electric transmission and distribution utilities are regulated by the states and also by the federal government. And so each state has its own regulatory agency. And so I worked for New York State's regulatory agency, and I worked very closely with electric distribution system planners from all of the New York utilities like Con Edison and National Grid and et cetera. And after spending about 6 years there, and really my focus there was mostly on distributed energy. It was on smart inverters and battery technology, and essentially ways to, I guess, democratize the grid. So one of the really like key points of what was occurring in New York was the New York REV proceeding, stands for Reforming the Energy Vision. And that started around 2013, 2014 timeframe. And the vision there was, distributed energy resources are becoming more and more popular, and they're no longer just tools for a hobbyist. Rather, they're more becoming the day-to-day, right? Like could potentially see solar on every rooftop and energy storage systems in every utility closet of every building. And we're starting to see it now, right? With in California, we're starting to see the building codes change, where every new building has to have solar on its roof. And as these technologies get less expensive over time, and as their capabilities increase to become increasingly useful over time, I think we're going to see not only new buildings with this type of technology, but existing buildings get retrofitted. And so it's very possible that we could see a future where every building has some sort of DER, right? Some sort of rooftop solar with energy storage and maybe a wind turbine somewhere, and controllable loads. I think controllable loads are really the next big frontier to tackle. And we're starting to see now, if you go to Home Depot or whatever, you're starting to see appliances with, smart appliance technology, right? Where they can respond to price signals. And we've seen a number of utilities do pilots with hot water heaters and things like that, where you can control HVAC equipment and hot water heaters and toggle them on and off and whatnot. And I remember when I was in New York, they would often, there was a mantra there, right? Where the least expensive form of energy is a negawatt, meaning a negative watt, which is power that you don't use. That is far less expensive than building out capacity to serve power that you do use. And we can get into talking about peak load and annual usage and things like that. Actually, let me get into just a little bit of that now, because really a lot of what was happening in New York kind of set the stage for what was occurring, or what occurs in the rest of the country. So I've got a whiteboard here, and I think we can see it pretty good. So when you look at just a load over the course of 24 hours, it looks something like this, where you have a small peak in the morning, and then a bit of a trough in the afternoon, and then a large peak in the late afternoon and into the evening, and then it goes down, and then it's relatively low overnight. And so if you look at the peak that occurs, which is up here, the entire grid is built to serve this peak on the highest load day of the year. So you figure January, or not, I'm sorry, not January, but like, let's say July 15th, the hottest day of the year at 4:30 p.m. or something, when the most electricity is being used. there is a system peak. And in New York, that was something like 40,000 megawatts or something like that. However, the average usage was half that. So if you wanted to take the annual sales of how much power a utility used, you could basically take what, so if the peak's 40,000, the average is 20,000 megawatts, multiply that over the number of hours in a year, 8760, and that gives you the number of kilowatt hours utilities in the state of New York moved over the course of a year. However, the peak is something different. And, it's interesting because if you look at annual usage year over year, it remains unchanged. If it does grow, it just grows by a small fraction of a percent. But if you look at peak load, this peak right here, that grows every year by like 4% or something like that. And so essentially you have to build out more and more infrastructure, more and more capacity to be able to serve that peak load. And that is extremely expensive. And it's interesting because you're not spreading that cost over more kilowatt hours. At the end of the year, you sold or you moved, depending on the model of the utility and their regulatory regime, they moved the same number of kilowatt hours. However, they keep having to expand that grid to meet the peak. So the idea of a negative watt, a negawatt, which is basically where, okay, it's peak energy is extremely expensive. Let's go ahead and push our usage out to some other time, either overnight or in the middle of the day when solar resources are ample or something, anything other than the peak. And as I would imagine, probably most of this audience is aware, is the duck curve, where when you have ample solar resources, that's really great in the middle of the day. However, for the evening peak, that occurs just as all the solar resources are coming offline. So, in a place like California, you essentially end up having to ramp up, I don't know, something like 50,000 megawatts or something on peak load day in the matter of about 30 minutes to go from all of that load being served by solar to the solar dropping off to the load increasing to peak, and then now all those fossil and nuclear resources having to ramp up. So California has been heavy on the batteries, pushing battery technologies and pilots and things like that, which we've seen in Southern California, Edison and elsewhere, where they're deploying utility scale batteries, multi-megawatt batteries, to try to essentially keep from having to upgrade substations. If you want to build a new substation today, which the whole purpose of that would be adding a new transformer or something, you're looking at, millions of dollars, possibly 10, maybe even more $1 million to build a substation, maybe $15 million, something like that. And that just serves like a small area. So by having these batteries, sort of at the intersection of where transmission meets distribution or somewhere along the transmission line, you can do a lot in terms of not having to build out the rest of the grid. So I just wanted to kind of set some of that backdrop. And also, I wanted to mention that probably most of my talk really is kind of unrelated to my work at PPL. I'm not here speaking to you as, the corporation or something like that. The remarks here that I'm making today don't represent PPL, right? I'm an engineer in the industry, just telling you what I've learned. And so I really do want to set that context that, the examples that I'm talking about are from all over the world. And if I am talking about PPL, it's really just in the sense of an example. So please don't take my remarks to be representative of the corporation. Okay, so that's some of the background. Just relating that back to what I was saying about New York State is they had a revolutionary project, and this was back probably 5 years ago now, called the Brooklyn Queens Demand Management Program. And so this utility, Con Edison, a Consolidated Edison Company of New York, they serve New York City and some of the surrounding area like Westchester County. And Con Edison needed to increase grid capacity in this one particular neighborhood called Brownsville, and it's on the border between Brooklyn and Queens. And it was a neighborhood that it was in the process of gentrifying, and as a result, load was increasing. So Con Ed, just using the traditional way of how they do things, how utilities do things in general, they looked and they said, okay, we need to increase capacity. What does that look like? Well, to us, that looks like building a new substation. So they did an analysis to determine how to build out capacity. So there was an existing substation in the neighborhood, and what they were going to do was purchase the property that was adjacent to the existing substation, level everything that was on that property, and then build an expansion to their substation, like a new transformer and things like that, that would add, another 10 or 20 megawatts worth of capacity. And that ultimately, between the real estate acquisition and the purchasing of the equipment and the installation and all of that, and mind you, in Con Edison, where property values are very high, they're not just using, air as an insulator like you would see in a substation. They're using SF6 technology to minimize all the equipment, stuff like that. At the end of the day, it was going to cost $1 billion with a B dollars to build a substation. So that's one thing that I had worked on when I was in New York State, was the Brooklyn Queens Demand Management Program. And there we worked with Con Edison to see, hey, is there a more cost-effective way to do this instead of building out a new sub? And so they got creative, and very, very creative. It was an excellent project where they went and they talked to all of the customers in the on the affected circuits where they needed to increase capacity, and they needed to increase it first by about 10 megawatts, over the course of a year or two, and then another 10 megawatts a year later, things like that. So you could have an incremental approach in this particular problem that they were trying to solve. So ultimately, what they ended up doing was going through with an energy efficiency program and reducing load on, from the customers that are on that circuit. They did some demand response as well, found some customers with some flexible load that they could leverage during peak conditions. And then I'm going to kind of oversimplify it here, but they also went halvesies on a battery with a customer, where they basically said, hey, look, it's in our interest to deploy this battery in this particular area. That would help us with our capacity constraint. And the customer also could use the battery because they can use it to reduce demand charges and save money on their utility bill. So it's a win-win for both the utility and the customer. The utility would use it during peak time where they needed it for capacity. The customer could use it the rest of the time. So anyway, you add all that up, and for a fraction of the cost, talking like 10%, not even, of the cost of building a new substation, they were able to meet that capacity constraint. So that just kind of shows you the effect that DERs can have. I mean, it saved the customers of New York City like $900 million, right, to use DERs instead of building out the more sort of traditional capacity. So that's a really fantastic example. Was extremely proud of that work coming from New York, and it was essentially the flagship project. How applicable that is to the rest of the state, particularly rural, like really spread out areas, different. Everything's different, right? Every situation is different, but that one particular example has always stuck with me, and I wanted to share that with you all. You can Google it. BQDM, the Brooklyn Queens Demand Management Program. It's a few years old now, so you can see how it's evolved over time. But anyone that's interested in looking that up, I highly encourage you to do so. So that's essentially the backdrop. Now let's get into some more detail. So I just want to share real quick some of the highlights from my time at PPL. My screen here. So as Rudy had mentioned in the introduction, this was my team here winning the 2019 Utility of the Year award from the Smart Electric Power Alliance. Extremely proud to have won this award. That's me over here on the left. And then later on that year, we won Top Innovators of 2019. And so the SEPA and the Public Utilities Fortnightly Top Innovators Awards, those were in response to our DERMS system, building out our DERMS system. So extremely proud of that. And then in 2020, we won the Foremost Innovator in Distributed Generation of the Year 2020 award. Again, extremely proud of this. This was for the development of our DER management device. So this is all of, I wanted to kind of highlight some of that because that's what I've done since last addressing this audience. So, extremely proud of this work that we've done and the opportunities that PPL has given me. So thank you, very much. And that's probably enough on my background. Let's see, let's get into the talk here. So I want to talk a bit about, I have my notes here. I want to talk about the IEEE 1547 standard and the evolution over time. So DERs have historically been essentially a tool used by hobbyists. You got to figure the first solar panels came out in the 1970s, something like that, and have evolved over time. And back then it was such a small percentage of customers using these things, just a few customers here and there in entire regions, where utilities really more treated solar as like some sort of nuisance than really an asset to be leveraged. And all that has changed over the last couple of decades, but just wanted to share with you where we started. And as solar started to get more affordable and increasingly popular, in 2003, the industry coalesced around the IEEE 1547-2003 standard. And that standard really was just about safety. It was about anti-islanding, which is a concept I imagine you all are at least passingly familiar with, which says that, look, if the grid goes down and you have some sort of generation resource behind the meter, it's a safety issue that you cannot export your power onto a de-energized grid, because you could have linemen out there working, you could harm, injure, or even kill them if they're in the wrong place at the wrong time, right, where you're exporting power onto a de-energized grid. So 2003 standard was really about anti-islanding and safety and tripping and things like that. And then as the technology got more popular, right, because it became increasingly affordable, increasingly capable, the standard started to evolve with it. So if you fast forward to 2015 timeframe, somewhere around there, you started to see grid support functionality get included in the IEEE standard. So those are things like the ability to turn the device on and off and adjust its power factor setting and things like that. And the most recent revision of IEEE 1547 is the 2018 standard. And 2018 is really magnificent. It has a robust suite of grid support functionality, and we're going to get into some of the details of that as this talk goes on. But really, more importantly, or not more importantly, but just as important, is 1547 2018 standardized communication interfaces on DERs. So essentially what that means is you have this DER, let's take a smart inverter on a solar array. You have a DER and it has a suite of grid support functions that can help utilities with supporting frequency and voltage and things like that, just power quality type issues. And you need to be able to leverage that functionality. And until 1547 2018, it was sort of the Wild West. Inverters could have communication interfaces or could not have communication interfaces. Those that did have communication interfaces, you could use whatever protocol you wanted. Many of them used Modbus, and then 2030.5, which is also known as SEP 2, Smart Energy Profile 2.0. That started to gain traction. We started to see utilities beginning to use 2030.5, and a lot of that was pushed out of the regulatory policy of the state of California, which had some requirements around that. I would encourage you all to look up California Rule 21 and the different phases of that if you're unfamiliar. Or the inverter could use a completely different interface entirely, like 61850 or DNP or anything, right? Could be anything. So the 1547-2018 standard said DERs, and that includes solar, any sort of dispersed generation, energy storage, things like that. Doesn't quite include demand response or anything like that. So it really is a generation and energy storage standard, at least so far. It said, look, thou shalt adopt at least one of these standardized communication protocols, either Modbus, specifically SunSpec Modbus, and we'll get into examples of what all that looks like, 2030.5 and DNP3, and I've got a lot of really great resources to show you guys on that. And the IEEE standard, it's a whole body, it's standards association that makes these standards. So you have folks from utilities, you have folks from the solar community, both solar advocates, as well as solar installers, solar equipment manufacturers, and even larger corporations. Lots and lots of players involved in this standards association. So when they use the term coalesce, when I say the industry coalesced around this standard, it really is just that it is representative of anyone who wants to participate. It's all very open. So I would encourage any of you that are interested in any of this to go to the IEEE website, check out the Standards Association, and get involved in the working groups. You can get involved in the 1547 working group, for example, or the 2030.5 working group, or whatever working group you wish, and you can help shape these standards. And that's one thing that I wanted to push throughout the course of this talk are actionable items for the Lehigh University students and really anyone who's watching this. Things you can go and do today, right? You don't need to wait until you've graduated or gotten a job in the industry or anything. You can start educating yourself on these today. And by putting something like, hey, I'm in the IEEE Standards Association and I'm on the 1547.1 working group or whatever it is, you can throw that stuff on your resume, and it will signal to employers that, look, you are serious and you're doing your homework. You're not waiting for someone to tell you what to do. You've gone out and proactively started learning the skills that you'll need to apply once you join the industry. So throughout this talk, I'm going to try to nudge you guys and nudge you all into doing things like that. So let's talk about Hawaii. I'm going to share my screen again. There it is. All right. So here's Hawaii. Very interesting situation here in Hawaii. You have all of these different islands, and each island is its own independent grid. There isn't transmission between them. So every grid is its own, literally its own island. They're not connected to each other. They can't lean on each other for inertia or grid support or anything like that. And so on each of these islands, you have a power plant or maybe a couple. And it's interesting with the way these power plants work. A lot of them are oil burning, and the way the Jones Act works, which is a federal policy that I really despise. The Jones Act says that anything going to an island owned by the U.S. needs to come from the mainland. So ships like coming from Japan or whatever elsewhere, Middle East, whatever it is, they can't first stop in Hawaii on their way to the mainland to drop off oil for the power plant. Instead, they have to go to the mainland first, and then come out to the islands. And that makes the fuel even more expensive. So you were already shipping in the fuel, but now the Jones Act makes it even more expensive because you first have to stop on the mainland to satisfy those regulations. So as a result, power in Hawaii is extremely expensive. You're talking, multiple times more expensive than it is on the mainland. And also you have an abundance of solar resource. So as a result of the high price of energy from grid service, the economic prospect for customers to deploy solar resources at their homes is very high, very good payback periods. So what you saw, and then plus on top of that, all subsidies like the industrial production, I'm sorry, the industrial tax credit, production tax credit, net metering policy at the state level, on and on, right? So you saw an absolute explosion in the adoption of solar. And so really, if you are unaware, Hawaii is essentially this wonderful case study where we can see what it looks like when you have a high penetration of solar relative to other power resources. And so, you know, it's interesting. Let me draw a little bit on my whiteboard here. So in Hawaii, and let me just move this here. There we go. All right. So in Hawaii, you have, you know, your sort of typical load that I was just showing you, where, you know, you have your morning peak, your afternoon trough, your evening peak, and then the overnight trough. And the oil burning power plants that are there on the island were designed to load follow. So let's say it's a smaller island, you have one power plant. That power plant was designed such that it can follow the curve here. So as load goes up, the power plant can ramp up. As load goes down, it can ramp down, and it will just, it's a technical term called load following. And that worked really well for a long time. Well, solar resources started to get deployed. And so if you look at what the generation profile of a solar resource looks like, is on a perfectly clear day. You obviously have nothing overnight. And then as the day goes on, your solar resource produces more and more energy. You have a peak around noon, and then that goes down. And then with, you know, by the time you get to the evening, it's dropped off. That is what a perfectly sunny day looks like for a solar generator, like a rooftop resource. However, when you have an intermittently cloudy day, what that looks like is, let me draw what it looks like on a perfect day. On an intermittently cloudy day, where, you know, you have a cloud come over and then leave, and every few seconds it does that, your solar resource essentially looks something like that in terms of the amount of power that it's producing. So now let's talk about this in terms of what that oil burning power plant is asked to do. You went from, you know, that nice, you know, slope, that like kind of double hump slope there with the morning peak, afternoon trough, evening peak, to essentially that something that sort of looks like this, and then afternoon, and then evening, and then overnight, right? Something like that. So you can tell that this is a lot more demanding on that oil power plant. The oil power plant was designed to do something like that, not follow up and down as the solar resources ramp up and down and are able to serve behind the meter load to varying degrees. So once you start, like on an intermittently cloudy day, once you start seeing this sort of violent ramp up and down of resources, that power plant just cannot keep up. And so as a result, you have frequency problems, you have voltage problems, you have, you know, situations where voltage essentially collapses on the island, or frequency collapses. And you have lots of infrastructure connected to the grid. And when that infrastructure detects changes, you know, abnormal changes in frequency where they get to be outside of acceptable ranges, they trip offline to keep from damaging their equipment. So for example, spinning machines, you know, when frequency is sort of violently going back and forth, you could cause damage to power plants, things like that, on the actual machinery. So as a result, these power plants will trip offline if frequency or voltage goes too far out of whack. And so as a result, you started to see blackouts And so when I say that the industry coalesced around some of these grid support functions and communication interfaces and things like that, it was really to start to address these types of issues. Thankfully, you know, I imagine most of you are all in Pennsylvania. We are on the Eastern Interconnection, which is most of the Eastern United States. And it is a lot of inertia. So if you have intermittent solar resources in one area of the country, it's really not a big deal. You have this big interconnected transmission grid, and you know that's fine. But in Hawaii, it's a very, very different story. So everyone sort of looks to Hawaii to see what does the future look like? What does the future look like where you could serve somewhere close to 100% of your load from behind the meter resources? And then when those behind the meter resources, if they are intermittent in nature, are no longer available, what does that look like? So the IEEE 1547-2018 standard begins to try to address that. And we are starting to see you know, adoption in various jurisdictions across the country of that or similar standards. Like I said, Rule 21 over in Hawaii, over in California, Rule 14H in Hawaii, and then other jurisdictions throughout the country adopting standards as they see it's appropriate. So that is Hawaii. Let's see. So I want to talk about some of the specific grid support functions. So let's start with volt var and fixed power factor. Just consulting my notes here. Yeah, okay. 1236, okay. So let's talk about volt var. So one of the grid support functions in 1547-2018 is volt var. And if you are unfamiliar, it looks like, the curve itself looks something like this, where you have grid voltage along the bottom, and then you have reactive power support along the y-axis. Reactive power support. Okay, so when grid voltage is, I'll just put an N for normal, when it's in this sort of normal range, we are asking the DER. So this is the volt var, it's a grid support function. It's in IEEE 1547-2018, and DERs are required to have this functionality. So that's the background. So when grid voltage is normal, and you can define curves are, you would say, I don't need any reactive power support. I'm in this normal zone. I don't need help from this particular smart inverter. So go ahead and just produce all real power. You don't have to produce any reactive power. We don't have a need for it. However, when grid voltage is low, you could say, actually, now I do need you to give me some reactive power. So give me, let's say, you know, plus 44%, and I can show you where that number comes from, but it's just a relatively common number that you might use in a volt var curve. So give me 44% of your nameplate capacity in the form of reactive power. And we can get into reactive power versus real power, things like that. I can draw the power circle and show you technically how some of that stuff works. But so, you know, this is just kind of a quick little introduction. And then when grid voltage is high, what I need you to do is absorb reactive power. So give me negative 44%, just for example, just trying to put the numbers here. And if you're unfamiliar, by injecting reactive power, and reactive power is measured, the units for it are bars, volt amp reactive. So capital V, capital A, lowercase r, volt amp reactive. It's basically the reactive version of a watt. By injecting bars onto the grid, you will raise grid voltage. And by absorbing bars, you will lower grid voltage. And so the industry saw that things like volt-var curves or even fixed power factor settings, which are sort of related to a volt-var curve, that is an extremely important feature that DERs need to have in order to support a sort of healthy grid ecosystem. And it's really interesting how reactive power works. So let me draw the power circle for you. So when you have a piece of equipment that either produces or consumes power, you have a power circle, and then that circle is divided into quadrants. And then over here on the right hemisphere is where you are producing power. And then over here in the left is where you are consuming power. And then on the top, you have injecting reactive power. And then on the bottom, you have absorbing reactive power. So this axis is reactive, and this axis is real and reactive power. And so when you are a smart inverter on a solar array, you're not consuming any power, you're just generating power. So this whole half of the circle just kind of goes away. And really, we're just talking about this half of the circle. And so when an inverter is producing power, generally it's just going to produce real power because that's what you get paid by, is your kilowatt hours. And so inverters generally will just produce as much real power as they can. Let's say it's a 10 kilowatt inverter. So on the sunniest days of the year, at the sunniest time of the day, that inverter is going to be producing 10 kilowatt hours. And then in the middle of morning or evening, or on less sunny days, it's going to be producing somewhere less than that. And then at night, it's producing 0. And then when a smart inverter is loaded to have a volt-var curve or a fixed power factor setting or something like that, then what happens is you're no longer just following this line, but rather you change the angle. So let's say we could change the angle so the new line looks like that. And so when people talk about power factor, oftentimes they refer to the cos phi angle, the cosine of phi. And this angle here is phi. So you have the cos of phi and then some number of degrees in there. And it's interesting because if you were to, I used the example of 44% earlier. So essentially what's happening here is you've gone down on this curve a little bit, which means you've backed off of the absolute maximum amount of power that a smart inverter can produce. So you're no longer producing 10 kilowatts, but let's say in this example, you are producing 9 kilowatts. However, if you bring it out to here on this axis, you end up producing 4.4 kVAR. So essentially, it's just trigonometry. You can figure it out with this angle and the Pythagorean theorem and whatever equations like that. But by sacrificing 10% of your real power production capability for a voltage support function, you gain 44% of reactive power capability there. And so I think that that's really profound. And when you're talking about grid support functionality, I think the voltage support functions, particularly when you're on a distribution system like outside of Hawaii, for example, the voltage support functions are really, really, really critical. And this concept of a slight sacrifice in real power for gigantic gains in reactive power is a very important concept that I think people working in this space need to understand. So again, by sacrificing 10% of the amount of real power that you produce, you will gain 44% in terms of nameplate capacity of an inverter in reactive power. And you can either absorb reactive power or inject reactive power. So that's how a volt bar curve or a fixed power factor setting would work. And then just to show you where something like this would be extremely useful, it would be during lightly loaded conditions. So generally you have, I'll draw for you a voltage profile of a distribution circuit. So this is just a circuit for a distribution utility. And then this x-axis along the bottom, this is distance. So I'm just going to put a D for distance. And then distance 0 is your substation, so SS period. And then the end of this axis here is the end of the feeder. End of feeder. And so typically what happens is I admitted earlier during this talk that I went to school for civil engineering, I think in terms of water pressure. So when you're coming out of the substation, your voltage is really high. Just like if you were coming out of a water source through a pipe to feed water to houses or whatever it is, you need that pressure to be really high at the source, because as you go down the circuit, customers are going to consume power, and that reduces voltage, just as how if you were consuming water out of that pipe, it would reduce pressure. Same sort of concept. So during the winter and during the summer, power usage is extremely high. So voltage drops very quickly. And so essentially what you'll do is coming out of the substation, voltage will drop pretty quickly. The distribution utility will install like a capacitor bank or a voltage regulator or something like that to raise the voltage back up, this voltage, and then it can continue on down the feeder. So that's what the voltage profile of a distribution circuit would look like during winter peak or summer peak. However, during the spring or during the fall, the voltage profile looks very different, because consumers really aren't consuming that much energy, right? You got to figure your HVAC loads are off. You are at work, so there's basically no loads in your house. Essentially, the only thing that's running is if you have an electric hot water heater that might kick on once in a while, as well as your refrigerator. But that's really about it. All the big loads in your house are off. So this is what a voltage profile would look like during a nice, 70-degree spring day or fall day or something like that. And then when you start interconnecting solar resources, again, there's no load behind the meter for that solar resource to satisfy. So essentially all of the energy that you are producing just gets injected onto the grid. And that results in an increase in voltage. Imagine injecting water into a pipe. You are going to increase the pressure of the water in that pipe. So essentially, if you had a solar customer here, interconnect, that would raise voltage during that spring scenario. And then the new line looks like this. And then if you had another customer down the circuit a little further, install solar. Now the spring scenario line looks like that. And then if you have another customer later injecting power, voltage continues to go up as you have more and more customers injecting power onto the grid. And utilities have a tight band by which they can serve power. So let me use the red marker here. And so you have to give power to customers that is plus or minus 5% of nominal. So if you were to, if you're at your outlet and your wall, that's 120 volts. Plus or minus 5% is between 114 volts and 126 volts. So the utility has to provide you with power that is in that range. And if you have situations where a circuit, just goes gangbusters, to use an old term, on installing solar, you can see the voltage creeping up and up and up. And then here you have a situation where during this spring day, you now have a voltage violation. Voltage is now 128 or 130 volts or something like that, when the maximum that you were allowed to provide was 126. So in the absence of standards like IEEE 1547/2018, utilities have been extremely conservative in the amount of solar that they can allow to interconnect to their grid, because if they hit a voltage violation like that, well, it's the utility's responsibility to ensure that voltage violations don't occur. So utilities historically have been conservative in the amount of solar that they would allow to interconnect to the grid, because there could be situations like spring and fall where the production of solar and export of that solar onto the distribution system would reduce power quality for the adjacent customers, potentially damaging your neighbor's equipment or utility equipment, things like that, because they were not rated for such high voltages. So you could damage them, or they could trip offline, or whatever it is. So that's I just wanted to close the loop there with you and show you why voltage support functionality is important. It's important because essentially and you can look up studies that were done by Duke, as well as the National Renewable Energy Laboratory, Arizona Public Service, EPRI, etc. There's a whole series of reports that you can look at that show that when DERs are able to provide voltage support functionality, you can often double, sometimes even triple your hosting capacity, which is the amount of solar that you can put on the distribution system without having to require upgrades. And upgrades can be very expensive. So if a distribution utility needed to install some equipment to bring voltage down, a voltage regulator, for example, that's $60,000 or something like that, right? So imagine you're installing a $10,000 or a $20,000 solar array, you apply to interconnect, and the distribution utility says, okay, you can interconnect, but it's going to cause a high voltage problem. And the only way we would allow you to interconnect is if we install this voltage regulator. And because you are the customer that is causing that issue, you would have to pay for that voltage regulator. So now all of a sudden the economics of the homeowner go from, okay, I want to install a $15,000 solar array, but in order to do that, I'm also going to have to pay $60,000 for a voltage regulator. Well, that project is very quickly not economical. So by requiring, as the IEEE standard has done, voltage support functionality within smart inverters, you can drastically increase hosting capacity, because what you would do is through a number of methods to do that, whether and different jurisdictions around the country are doing this differently, right? Like some utilities are doing it directly. Other utilities, like in California or New York, are working with aggregators or third parties in the middle. I really don't. It doesn't matter how you do it, just as long as you are able to send that signal to those DERs to say, hey, look, I need you to adopt this particular volt bar curve with these points, because this is the voltage that I need you to have, and this is the conditions under which I need you to provide reactive power support, things like that. All of that capability is now there. And so we can move forward as an industry where, instead of these resources sort of being at odds with each other, instead now they work in harmony, right? Where you have an electric distribution utility managing the utility-owned infrastructure, and you have customers with the distributed assets that best fit their needs and their values, whether they really like solar or they want to reduce demand charges, so they're putting in batteries, whatever it is. Now these two systems that were disparate are now able to work in conjunction. And as a result, we will have a much more affordable grid, allowing far more renewable energy to be deployed onto the system. So that's extremely important. And I'm just so proud of the efforts of the industry. I've participated in some of those IEEE working groups as well, at getting to this point, right, where you can have all of these factions within the industry, whether they be regulated utilities or solar equipment manufacturers or renewable energy advocates, all getting together and agreeing that, look, this is the path forward. By requiring that DERs have a particular suite of grid support functionality, and further that they have a standardized communication interface, we are going to be able to meet the renewable energy goals that this industry has, and that, we have, sort of based on your political jurisdiction, etc. So that's just sort of one example of voltage. You also have grid support functions related to frequency and things like that. And if you were to download either the IEEE 1547-2018 standard, which unfortunately does require purchase, and I unfortunately can't share it on screen because of copyright issues, so I just can only talk about it. But if you're able to get a copy of that, or look, there's a number of reports that different organizations throughout the industry have written on grid support functionality within that standard. Highly encourage you to educate yourself on that, because this, if you want to work in the electric power industry, this is the important challenge facing us today is how to leverage this support functionality. So I want to do about 5 more minutes of presentation and then get into Q&A. So let me talk about communications. Oh, let me talk about ride-through first. Ride-through is really exciting. So one of the other grid support functions is ride-through functionality. So this right here, what you're seeing on screen, oops. This right here was the old trip curve, essentially, for DERs. So what this says is, in this green band here, if grid voltage is, plus or minus, I don't know, maybe 7%, 8%, something like that, grid voltage is within that range, that healthy range, continue operating forever. Don't ever trip offline. However, if grid voltage starts to get weird, if it drops down to 80% of normal, right? So you're talking, maybe 90 volts at your circuit or something like that. If you drop down to 80% of normal, trip after, and this is a logarithmic scale, trip after 2 seconds. So, basically make sure that, if grid voltage has dropped down to 80% of normal and 2 seconds has passed, you absolutely must trip. And if grid voltage gets really wacky, like 40% of normal, I need you to trip off after like 0.2 of a second. So basically this green range says stay on, and then these darker pink or red ranges say you absolutely must trip offline. Again, this was all back to sort of the safety standards put into place with IEEE 1547-2003 revision. This is basically what that looked like. Everything else in between is a big old question mark. We have no idea what these devices are going to do. You can test and you can see, but there is no standard. They could trip, they could not trip, who knows? So, so PJM, which is a regional transmission operator, they operate all of the generators and transmission lines for Pennsylvania, New Jersey, where else? Maryland, and parts of West Virginia and Ohio and wherever. They're all over the place. A big, really big footprint. They did a study, and this was back in like 2018. And they said, okay, if this particular transmission line here in northern New Jersey were to have like a very brief issue where like it trips off for a second, or it has a voltage sag, or whatever it is, that would cause a cascading voltage issue. So basically all of the distribution systems within this footprint would experience a sag and voltage if this part of this transmission line were to experience an issue. So essentially what that looks like is a voltage sag in this yellow area that is big enough that it, based on the old IEEE sort of values here, it could potentially cause 1.2 gigawatts of solar generation to trip offline. And that was, 3 years ago now. So that number, who knows, maybe doubled. I'm not really sure. And so ride-through settings became very important, where we went from this to something like this. And it varies by jurisdiction. Each jurisdiction sort of has their own ride-through curves. Hawaii has their own, California has their own, New England has their own. Lots of jurisdictions are getting wise to this and starting to implement ride-through points. And basically it gives a solid instruction for what the DERs need to do. So when you look at this, Basically, you have, okay, if you're in this, plus or minus 10% here, stay on forever. Absolutely do not trip off. And if you drop down into a range down here, you must trip off. And then there's these other functions that are coming on. I don't want to spend too much time getting into all this. You can look up all this stuff on your own if you're interested in learning more. But basically, it gives PJM or whatever, whoever it is, in this case, PJM, but it's any transmission operator, the ability to calculate, okay, if I can model all of these resources, and 1.2 gigawatts is huge, right? That's like 2 gas power plants, or like more than 1 nuke power plant. And these regional transmission operators have reserves, they have contingencies, right? So they were prepared. PJM is absolutely prepared for this transmission line to go down. If that line goes down, no problem. They have spinning reserves somewhere else, or transmission from some other direction that they can use to continue feeding that power to where it needs to go. However, what the RTOs are not prepared for is the cascading 1.2 gigawatts of solar that would then trip offline. So before, let's say PJM had a power plant in place as a contingency in case this transmission line trips offline. Let's say it was carrying a gigawatt. You got a gigawatt of generation somewhere else that's ready. It's on standby. It's ready to jump in when needed. So that's fine. This transmission line trips, that contingency gets put into place. Everything's fine. They weren't prepared for another 1.2 gigawatts, or what's probably closer to 2 gigawatts today, to trip offline. So that's like 2 more power plants that they would have just spinning as a contingency. So it's extremely important that the grid operators understand what the resources are and how they are configured. When are they going to trip offline? And the old way of doing it, which is this chart here, just isn't cutting it. You need more precise charts like this. So I wanted to introduce that concept to you. Now let's talk about communication interfaces. So and I'll just go, I'm sorry, just a couple more minutes and then I'll do Q&A. So if you look at the communication interface, it's actually section 10.7 of the IEEE 1547 2018 standard. It says that, let me turn this off for a sec. It says that DERs shall have a standard communication interface, and through that communication interface, you can access the settings of the grid support functions. And that the communication interface needs to have one of 3 communication protocols, either Modbus, 2030.5, or DNP3. And I'll show you really quick what those look like, because I really want to encourage anyone who's interested in studying about this and getting involved to get involved. This is my specialty within the industry. This is what I've focused on for a number of years, and we need more people with expertise in this realm. The entire industry is dying for people that understand how to do this stuff. So I would highly encourage any of the engineers that are viewing this presentation to please consider getting involved in this area. You will be able to go wherever you want and work for whoever you want to if you understand how this stuff works. So I'll show you really quick what a Modbus interface looks like on an inverter. So these are screenshots from an application called Modbus Pole. So this is just a really simple, it's called a Modbus Master. It's a device that you would plug into an inverter's communication interface. You would set certain settings here. Hey, go to this IP and look at these Modbus addresses at the scan rate or whatever it is, right? You can adjust all the stuff as you need. And then here's there's like 3 different screenshots on this window to show you what it looks like. So when I want to read what an inverter is doing, I can take my computer or a radio or an internet connection, whatever it is. I can hook something up to this inverter and I can see what that inverter is doing. So I can see that it's connected at 59.997 Hertz. I can see that it's producing 27 kVA, and it's producing 10 kVAR, and it's at a 92.44% power factor and all that stuff. So this is actually what it looks like when you're communicating with an inverter. So on the top are its read points. On the bottom left, you have a volt-var curve. on the bottom right, you have a low voltage ride-through curve, and these are the values that you would manipulate to change the grid support settings. So you would say, okay, I want you to provide reactive power support at 97% of nominal grid voltage or whatever it is. So that's what your interface looks like. And then this is what the actual communication, so this would be a Modbus inverter. This is what they look like if you were to actually look at the machines talking to each other. So you have a request, which is this short message, and then you have a response, which is this longer message. Request, response, request, response. And that's the flow. That's how these machines talk to each other, is these numbers flow back and forth. And basically what it's saying is the request would say, hey, I am interested in reading these particular Modbus registers. Please tell me what the values in those registers are. And then the inverter responds that says this register is this value and this register is that value, on and on. And I can show you one other thing that you can do right now, for free, students that are interested. You could download the documentation. So for example, this is from a Fronius inverter. This is its Modbus map. You can download this documentation on the website for free, and you can say, okay, so over here on the left, these are the Modbus addresses, and these are the functions associated with those addresses, and these are the units that you're going to see and stuff like that. So when you want to read voltage, you would say, okay, I want to see what my phase A to B voltage is. So you would go to this Modbus register, and then you would ask the inverter to give you the value of what's in that Modbus register, and then it would spit it out. It would say I'm at 120 volts or 240 volts or whatever. So you can download this documentation from the inverter manufacturers. Most manufacturers have it there for free. You can just Google it, or you could, or you might need to write them. Just write them from their help, their contact page, and ask for this documentation. And generally, they'll freely share it with you. So again, students that are interested in gaining a mastery of this, highly recommend you start looking at this. Let's see, this is what 2030.5 looks like. So this is a tester made by Quality Logic. And basically you put in some settings and it kind of tells you some stuff. And this is what 2030.5 looks like when you're communicating. It says, okay, this is just a message. Oops. This is a message from the inverter saying, hey, for apparent power, which is VA, I am producing 103 VA. And it'll tell you what your if you have a multiplier on there and whatever, things like that. So this is what 2030.5 looks like. Highly recommend that you all download the 2030.5 standard, IEEE 2030.5, and you can start learning how this works. It's in English. It's actually really easy to understand. It kind of looks like HTML. And then the third protocol is DNP3. So that's what this is, a DNP document you can download. And basically it says, okay, this DNP point has this function, active power. It's going to be measured in watts. And then you can actually go ahead and click. So that's analog input 537. So you would click analog input 537 and it'll tell you, okay, so this is power. It can go from this range to this range. It's measured in watts. And things like that. So this is all information that is readily available to you all today. And again, highly recommend that you begin checking it out. So I think with that, let's go ahead and jump into Q&A.
Thank you, Matt. Wow. So that's really wonderful. You covered so much territory. And so what I'd like to have first is the students in the audience. If you have any questions, please unmute yourself, introduce yourself, and go for it. And Matt, if you want, you can stop sharing your screen so you see everybody's face.
Okay, cool.
So students, unmute yourself, ask your question.
Hi, Matt. My name is Laura, and I'm a student in the ESE program. Thank you for your presentation. I just had a question. I was curious. You mentioned that before the grid support functionality, the utility would tell a customer that they needed to install a voltage regulator, and you mentioned that that's like close to $60,000. So I'm just kind of curious what the cost impact of the IEEE standard has been on inverters, and if including that sort of grid support functionality has increased the cost of solar systems and the inverters themselves.
That's a great question. What I've seen so far is the cost of inverters go down over time. You can get more and more capacity for less price as the years go on. You could buy like a small single phase inverter for less than $1,000 at this point. So it's hard to tell if the incorporation of that grid support functionality has increased the cost of the inverters at all, because they all just continue to drop in price. So I'm sorry, I don't have an exact answer for you.
No, I think that's helpful in my understanding. Definitely preferable to have the grid support functionality than pay a couple $1,000s for something mandated by the utility.
Absolutely, yeah. And you got to figure, like in places like Hawaii, their circuits are already highly subscribed, right? Like, so for example, in Hawaii, I think you could go on Hawaiian Electric's website, hawaiianelectric.com, I think today, and they have what's called hosting capacity maps. And they say, look, in these areas, which is a lot of Hawaii, you can't export power anymore. All the circuits are subscribed. You can no longer export power. We've done away with net energy metering there, which is a financial subsidy for these resources. We just can't handle more solar power in certain areas of Hawaii. However, they have done things like the CGS Plus, Customer Grid Supply Plus program, where in certain areas of Hawaii where you can still export without too negatively affecting power quality, you need to give the utility the ability to manage the grid support functions of those inverters. And then through that arrangement, through that agreement, then you are able to begin exporting power. So essentially what you saw was a hiatus, right? Like a stop to the exporting of power, or for at least new systems in Hawaii. Now, thanks to these grid support functions, you can once again begin, at least in some areas, to export power onto the grid. So it's really pretty fascinating. Again, I would point you to NREL and APS, Arizona Public Service, Duke, and others, APRI, et cetera. They've done a lot of hosting capacity studies you can look at.
Any more questions from students?
I see one from David in the chat. Power factor impact on SREX that can be earned by inverter operator. I can't really speak to that. I'm sorry. Any other questions?
Any other questions from students or otherwise?
And if we have another minute, I would talk about transactive energy just for a second, but I wanna prioritize Q&A.
Can you guys hear me?
Yep, we can hear you.
Okay, here's one from someone named KMR. Do most utilities use voltage limit to determine hosting capacity?
Oh, that's a fantastic question. So voltage limit generally is the limiting factor. However, it's not always. There's also thermal limits, which is really just the amount of current you can flow over lines. So generally, you're going to run into the upper bound of the ANSI voltage limitation, that plus 5% limitation. However, there are situations where you might run into a thermal limit instead. It's just less common. Any other questions?
Questions for Matt?
All right. And while, so I'll let people think about that for a second. One thing I do want to just mention, just looking forward, another really hot topic that I think students would really be interested in is transactive energy. So the Pacific Northwest National Laboratory, PNNL, they have been working on transactive energy for like at least a decade. And you know, there's a number of other institutions that are also working on it. And transactive energy essentially, and apologies if I butcher this, but from my understanding, essentially what it is it's a very robust marketization of the grid, where essentially what you have is, I can show you, let me pull up the SunSpec standard. So here we go. Okay, so if you go to sunspec.org, that is the website of the SunSpec Alliance. And earlier I was showing you a manual that I had downloaded from Fronius's website. Fronius makes inverters. And basically it was just, it was this Modbus map here, right? Like these registers go to these functions. And where all that came from was from the SunSpec Alliance. They built a standard for Modbus called the SunSpec standard. And you can look through here and you can identify all of the registers and the associated functions. So generally they start at a particular address, and you can look it up from your inverter manufacturer's documentation, what Modbus address they stop at or start at. So this would be like 40070 or something, and then you just add one to each function if you want to figure out what the addresses are. But anyway, you can go through here, and the 700 series, so those are the tabs along the bottom, all deal with smart inverters. So you can go through and you can figure out what kind of functionality smart inverters have. And so you can see here in 705, this is the Modbus model for Voltbar. So when you want to be able to program a Voltbar curve, you would come into here and you would manipulate the values that are in these Modbus registers in your particular device. And they should more or less follow this order, where they would say, okay, the number of points in the curve is 4 or 6 or 10 or whatever. This is when I want that function to time out, whatever. And then you have your actual points for when you're programming the curves, things like that. And then as you go on, you can explore all the grid support functionality. And just by reading the standard, you can start to get a sense for how it works. So here is the volt watt functionality. Here is low voltage trip, and you can go on and high frequency trip, and then eventually we'll get to, where is it? Let me go back to the old numbers here. You can get to price response models. So where are they? Okay, sorry, I don't have this teed up. But essentially, when you're going through here exploring, you can see all the different functions. And why this relates to transactive energy is there's a price curve where you can say, yeah, here it is, the price signal function. So basically, this says, look, if you are able to feed the inverter with information of what the price of energy is, it can do things in response to that. So essentially, like in the context of the forthcoming transactive energy universe, right? You might be able to have some sort of system where instead of having like sort of like a direct control, like this inverter, you do this, and this inverter, you do that, sometime in the future, we might be able to evolve to a point where everything just responds to price signals. And you can essentially say, okay, when price reaches 20 cents a kilowatt hour or kilowatt or whatever it is, do something. Start discharging your battery, because it'll be cheaper for you to consume the energy that's in the battery that you charged overnight than it would be for you to consume power from the grid. And if you look at like what Tesla is doing, is they have this auto bidder software technology that I believe they're going to roll out in their batteries. And essentially what it does is it looks like a stock trading platform. It's amazing. If you look at the auto bidder interface, it's got the candlesticks, the plus and the minus to show you how much the price of energy is changing from moment to moment. And it'll sit there and study it with AI technology, and it will learn what is the best time to charge my battery and what is the best time to discharge my battery. And there are experts within the industry that believe there is going to be a massive shift in where money is invested. And it's going to go from peaker plants, which, like I mentioned at the beginning of the talk, with meeting that peak that occurs on July 15th at 5 p.m., right? You have all this infrastructure built out just to meet that peak that only occurs a few hours a year. You're going to have, as batteries get more and more affordable and as people adopt them, and then as this auto bidder technology matures and gets incorporated into the battery systems, you could potentially have a system where all of the batteries across, your footprint automatically respond to price changes. And that's what triggers peaker plants to come online, is when price gets above a certain level, they start generating. And so instead of these peaker plants coming online, which are extremely expensive, and if you're worried about pollution, they are among the most polluting assets we have on the grid. Instead, you're just going to have batteries kick online, start discharging. And so essentially, you could have a scenario where we go from investing, hundreds of millions or maybe billions of dollars in these peaker plants across the world, probably trillion, huge numbers across the world, into batteries. And then the batteries, through this technology, this price responsive technology, be able to essentially obviate the need for peaker plants. And batteries are sited locally, so you don't have to have the transmission and all of that stuff. They can absorb renewable energy when it's being generated at inconvenient times, when loads are low, things like that. It's really an amazing future. So I had sort of started to talk about the internet revolution and how I see something similar happening in energy. I think we're going to see, I think that's going to be the catalyst by which we see that revolution. Really, really exciting stuff.
Wow. That's just simply, is this a work that Dr. Faruqi from Brattle maybe is working on, the dynamic pricing?
I have seen the Brattle, I think, Institute or whoever working on that. I don't have a mastery of their reports to be able to reference them off the top of my head.
Well, it is, as you say, it is the next revolution, and some of the resistance to it is maybe just behavioral. People are not used to, they're used to seeing one single rate, on a bill, and to see the variety of things that can be done. It's really fascinating. Any more questions for Matt? He's still around.
And please, anyone just unmute and start talking. But in the meantime, I'm just going to fill the blank space. Oh, Liam, did you unmute? Do you have a question?
Yeah, hi, I'm a student with the ESE program as well. And I guess my question is in terms of battery storage. So another thing that Tesla also has coming out is like the virtual power plant, which I feel like operates in a very similar way to battery storage, even if you don't have the battery capacity, where you can kind of control your own demand and the demand response. So I guess, what do you feel is a more viable solution in like the short term, battery storage versus virtual power plants, or do they kind of go hand in hand?
I think it's hand in hand. Yeah, I mean, I think the idea of a virtual power plant, at least from what I've seen, I know Con Edison has done some pilots, probably Endless Utilities have done pilots on this, or a large number anyway, where it's sort of like, for a virtual power plant, thinking in terms of a distribution engineer, to really be effective, they have to be related to each other in terms of geographic location and where they are on the grid. So if you have like some batteries at the head of the circuit, and you have some demand response assets in the middle, and you have whatever, an array of assets across a relevant, connected in some way piece of infrastructure, then a virtual power plant makes a lot of sense, because then you can say, hey, look, I need 20 megawatts of capacity here. I don't care how you do it. I don't care where it comes from. I don't care if that's a reduction in load or a discharge of batteries or a generator spinning up. It doesn't matter. I need 20 megawatts. Otherwise, the voltage is going to dip, frequency might dip, and I might lose the circuit, and these customers might be interrupted. So virtual power plants are extremely useful for that. And then, we're starting to see aggregation technology start to really take off. So I had mentioned the 2030.5 communication standard. It's so much more than communications. Within it is the ability to aggregate resources together and then offer those to control platforms as a much more sort of simplified interface, where you can say, hey, look, this isn't 100 inverters and 10 batteries and 20 megawatts of demand response. This is an asset that you can swing either this way or that. That's all you need to know.
All right, thank you. That's a great presentation.
Yeah, thank you very much.
We have time for one or two more questions before we let Matt go.
All right, we got one in the chat. When you talked about Tesla, were you referring to both automotive batteries and Powerwall? I was primarily talking about the Powerwall as well as the utility scale batteries. However, I do see electric vehicles starting to play a role in that. I think Europe's a little more ahead of us in terms of vehicle to grid technology. Most of the cars that I've seen, I think the Leaf maybe is an exception. There may be one other car. They're really just one-way flow, which is still very useful because an electric, when you as a residential customer buy an electric vehicle, your load increases by about 37%. And so if you are able to manage that charging, that is an extremely powerful asset. And so even just being able to manage chargers, I think is very important. And then once vehicle to grid technology starts to take off, where you can then start to discharge batteries to power the loads in your house or export that power onto the grid, then they'll very much act like power walls. But for right now, I'm mainly just talking about energy storage systems.
So one quick question, Matt. I know that Hawaii was having a lot of trouble with net metering and they suspended it. Is it still suspended or?
Yeah, if you go to Hawaiian Electric's website, you can see all of the different rate structures that they have. So yeah, it's I believe net metering is no longer in Hawaii. I don't know if I think they've grandfathered systems that came in under net metering. So you got to figure these customers made investments in solar arrays expecting, you know, a 5-year payback period with the net metering subsidy being a big part of that. So all of a sudden to change the rules mid-flight, I think a lot of states where they can grandfather their net metering customers are trying to do that. But we are seeing essentially the death of net metering across the country. I believe Hawaii, to your point, has gotten rid of it. I know Arizona and Nevada a few years ago had knockdown, drag out, brutal fights in the regulatory regime over getting rid of net metering, whether or not to grandfather customers. Because in Arizona, you had situations where 50% of customers were not paying a bill because they had solar and they were net metering, which means they weren't paying anything. And the other 50% having to pay for all of the grid. And so that was clearly not sustainable. So you saw Arizona and Nevada start to back away from that. California, I believe, is backing away from net metering. Minnesota with their value of solar project. New York with their value of solar as well. Or value of BER. VDER, that was the proceeding they did, VDER. So if you want to look that up at a New York State Public Service Commission, a lot of states are backing away from net metering.
So what's the incentive for new customers to install solar then?
Well, you can still export technology. I'm sorry, you can still export power, and also you can reduce your load. You know, if you're, and it really time-sensitive rate structures, I feel like are just so important. If you look at, like, for example, in New York, where I came from, residential customers, unless they opted out of this regime, essentially they paid a monthly average. So, for example, in the month of July, it's actually a really important point. In the month of July, you would use, 1,000 kilowatt hours in your home. And then they take the average price of power in the month of July, multiply it by 1,000 kilowatt hours, that's your bill. However, on July 15th at 5 p.m., energy, and you can look this up on the New York ISO website, is $20,000 a megawatt. And at midnight, just later that day, it's $20 a megawatt. It's 1,000 times more expensive for energy, but you don't see that, you don't feel that. However, once we start to evolve rate structures to represent reality, right, what's actually happening on the ground in terms of physics, then you will start to see the smart appliance industry starting to develop demand response assets within, their appliances and things like that. You'll really start, when you feel a 1,000 times increase in the price of something, you will react. However, customers have largely been insulated from that. As a result, peak loads continue to grow. And as a result, the utilities continue to have to invest in more and more capacity to meet that peak load that only occurs a few hours a year. And it is insanely driving up costs. And so it's really in the industry's best interest to start becoming sensitive to not only like location, but timing. And this is really where transactive energy comes into play, is you could have a time-sensitive nodal pricing structure where every node along the grid has different constraints, different factors, the ability to get power there or not get power there, and then time of day, right? In the middle of the day, power is one price, overnight it's another price. And essentially the transactive energy universe dreams of a scenario where every node has its own price, moment to moment price, and you can respond to that to keep the grid as affordable as possible.
Well, Matt, thank you. I still get comments on the chat line about V2G being a reality in Europe 2030. In UK, there's a tariff that gives negative pricing occasionally from Andrew. And of course, there are accolades for the talk that you just made. And thanks a lot on behalf of Lehigh University, Energy Systems Engineering. This is so engrossing, the talks. You covered so much interesting territory. Just a reminder, we have the last of the seminar series of November 29th. But I'd like to thank Matt for this wonderful presentation. And we will see the audience in a couple of 2-3 weeks, November 29th. And thanks for your attendance and look forward to see you guys soon. Thank you.
Thank you so much for the opportunity. Really appreciate it.
Okay, thank you.
Thank you, everyone.
Great job, Matt.
Thank you so much.